So this week we have Dr. Baker talking about the top 10 reasons why we should study topology.
Thank you. It's a pleasure to be here. Actually, I started thinking about this talk a year and a half ago when David was running the show, the graduate student. David's last name is? Page. Yeah, David Page. Right. And every year, every semester, I seem to get screwed up in some way and didn't get it on the list. So this is it. I have never given it before and probably will never give it again. Now, keep an eye on my hand as to which hand is holding the control. Because if I move it to my right hand, I have Parkinson's, and so it moves a lot. So we'll get through real fast. If I start carrying this controller in my right hand, we'll be through in about 5 minutes, okay? We'll get through it. Hey, how you doing? Come on in. First, let me say this is intended to be both instructive and giving you some insight into topology and also a little bit of fun. Okay, so this is somewhat tongue-in-cheek at times, and come on in. Unfortunately, it's getting a little crowded. Marong has been a terrific help. We're going to talk about these 10 reasons why everyone should study topology, and he has no responsibility for picking them. He just made everything work if it works. Any mistakes are my own, but he's been very helpful. So we can stop and answer questions at any point, and if it seems like we get only to number 7 and it's time to quit, you can tell me that. All right. Okay. There. Okay. I'm learning. Okay. At least I don't have it in my right hand. Keep it out of my right hand. All right. This is a talk that's intended for the aspiring topologist or anyone else who would like to know a little bit more about it. The point is not to make everybody a topologist, but the point is that everybody should study a little topology along the way, maybe a little bit more than a little. And what these 10 reasons are, I hope will give you some insight into that as to why. Number 10, reason number 10, is where we live. R.L. Moore Hall, come in. R.L. Moore Hall is where we live. That's R.L. Moore, in case you hadn't recognized him. R.L. Moore got his PhD at Chicago from E.H. Moore in 1905, slightly over 100 years ago. And he was still on campus in an office, although he had been forced to retire when I arrived 42 years ago. And he was a very interesting character. We won't spend a lot of time on him, actually. There are two things that besides being sort of the name identified with our department in many ways, he was a topologist. There are two things that are identified with him directly. One of them is this example of a Hausdorff and completely regular space that's not normal. Now, how many of you have taken topology? So the rest of you have no idea what I'm talking about, right? Okay, when you start studying topology, there are various levels of separation properties. Different kinds of spaces have different kinds of separation properties. A Hausdorff space is one, if I can put this down. Yeah, a Hausdorff space is one in which if you have two separate points, you can get open sets about those that are disjoint. Any 2 points in the set, any 2 points in the space. Regular is a little bit more. You have a point in a closed set you can separate. Completely regular means that I can get a function from the space to the reals, which is 1 on a point and 0 on a closed set that's separate from the point. And this is an example of a completely regular space that is not normal. Normal gives you separation of disjoint closed sets. So this is an example that you would encounter in 367K. You might even come up with it yourself. The topology has standard open sets in the plane, appears upper half plane, including the x-axis. Open sets in the plane are just the basis you can think of as disks, open disks, and take the unions of those to make open sets. But the points on the line are different in the sense that their neighborhoods are a point together with an open disk that's tangent at that point. And that's what gives it its characteristics. And we won't go into the depth of the why and how you prove that, but We can talk more about that if you wish, but that's the Moore plane. If you have questions about it, we can talk about that. So let's move along. The thing he's probably better known for, most often known for, is his technique of teaching. And have any of you taken a Moore method class? So you know what we're talking about. Have you ever seen Moore on tape? Would you like to? Okay. Let's see if we can make this happen. So I need to get my mouse with my left hand. If I can find the mouse on here. There he is. This is a very brief video of R.L. Moore talking about his teaching philosophy.
A foreign mathematician was visiting the United States some years ago, and we were talking, and I told him that sometimes when a student gives a long proof and I see a short one, I don't tell him about it. He said, why, if you know a short one, you ought to tell him. If you don't, you're not teaching. If you don't, you're not teaching. I'm tempted to paraphrase a well-known statement about government and say that student is taught the best who is told the least.
So there's your snapshot of R.L. Moore and his teaching philosophy. Are y'all familiar with his teaching philosophy? Is that encapsulated pretty well? He was a crusty guy. He was crusty is probably a dramatic understatement. He was known to actually ask other faculty members to go out and settle a disagreement in fisticuffs, even when he was in advanced stages of age. This is the man for whom our building is named. So when you think about topology and you think about this building, think about R.L. Moore. Number 9 is topology brought us R.H. Bing. R.H. Bing was a student of Moore, and Bing came here from Wisconsin. He was originally from Texas and got his degree here from Moore. And he was chairman of the department, and he was a force in bringing good people here and putting our department on a higher and higher plane. So we owe a lot to him. He was here until he died. I think he died at his desk. Maybe we all shouldn't necessarily follow that example, but depending on when you want to die. But R.H. was a great guy, and we enjoyed him very much. Here are 2 examples of things that he was famous for. He's famous for a lot. He did a lot. One of them is, that first picture is the dog bone space. At times in topology, there has been a focus in the past on decomposition spaces, where you would take a space like, in this case, R3, or the 3-dimensional space, and you would take subsets that would be then collapsed to points. So this is a quotient space of R3. This dog bone space is a quotient space of R3, where the individual points in the quotient space would be original points, or these arcs, or polygonal arcs, you can make them, that sit in the dog bone. And the importance of this thing is that when you take that, these are all nice sets, when you take that decomposition space, or you take the quotient space, it turns out to be not a manifold. Not only is it not R3, it's not a manifold. In other words, not locally Euclidean. But when you take the cross product of this with the line, with a copy of the reals, you get something that's homeomorphic to R4. So this is a fairly well-known example that's due to being called the dog bone space, I think in part because people like the name dog bone as much as because they like the example. Not many people work in decomposition spaces these days. This was probably, I'd say maybe 50 years old. This is called Bing's house with 2 rooms. The house with two rooms is a two-dimensional complex. That means it's got two-dimensional faces, one-dimensional edges, and vertices all put together. And this has the property that it is contractible. And I'm going to have to use these terms without giving you a lot of definitions. Contractible means it has the same homotopy type as a point. That means that it, in terms of a lot of algebraic topology, it behaves like a point. But it's not collapsible. Collapsible would mean that I had a free edge and I could start collapsing edges together and eventually get it down to something that would be like a point. So this is an example, the house with two rooms. Some people think it's not all that significant. There's also one by Zeeman. You know, some of you graduate students have heard of E.C. Zeeman, a British mathematician and topologist, who had another example like this of a dunce hat that is also the same properties. That is, it's contractible but not collapsible. Okay, so we'll move on from RH to number 8. It's good to know if you're on the inside or the outside. Here's Camille Jordan from the 19th century and early 20th century. And he had a theorem called the Jordan curve theorem. And the Jordan curve theorem basically says, if I take a circle in the plane that's embedded in the plane, then it has an inside and an outside. And the inside has as its boundary the curve, and the outside has its boundary the curve. And you might say, well, that seems kind of obvious, but try to prove it sometime. This is a theme that goes through several of the items I'm going to talk about as we go through this. But if you look at the general picture, here's one. It's not hard to tell. That's inside. Right? The difference, though, is when you look at something like this, and you say, okay, suppose I've got an undergraduate in here somewhere, and I want to know if he's inside or outside of the curve. That curve is actually a curve. It's a circle that I have drawn myself. I know it's a circle because I drew it. And it was not the first try. Okay? The first try, I actually had two ends that I was trying to connect, and one of them was out here and one of them was in here. And I don't know how in the hell am I going to get those two together? So I planned ahead a little better the second time. So we would like to know if I'm in here, am I on the inside or the outside? What do you think?
Inside. Outside.
We've gotten both answers. Okay. Well, here's one way to answer the question. Draw a line from the inside, not from the inside, from this point, that crosses all those lines and comes out. Now, why does that help?
Count the number of crossings.
Count the number of crossings. Suppose it's 15.
You're on the inside.
Then I'm on the outside or the inside?
Inside.
I'm on the inside. Okay. So how do I tell? If it's even, if the number of crossings is even, I was outside, and if the number of crosses is odd, I was in the inside. The only problem with this is, what happens if I'm tangent to one of these little dimples up here? You have to be careful. You have to get in what's called regular position, so that if I ever touch the curve, I actually cross the curve. You don't want a tangent, because this would be one contact with the line, with the curve, and that would screw me up if I'm worried about the parity of the count. Okay, so this is the Jordan curve theorem. We won't prove it. We'll leave it behind and go on to number 7. This topology that you do might help you with your number theory homework. Now, if some of you had number theory, some of you have been in my class in number theory. How does topology connect with this? Well, we can use topology to prove that there are infinitely many primes. Everybody knows what a prime is. Well, that's good. Okay, we're all on the same page. This is Harry Furstenberg, and this technique is called the Furstenberg topology on the integers. It goes like this. I take the integers, and I want to give it a topology. I want to say what sets are open and what sets are not. So I start with a basis, which will be the open sets that I'm going to use to build all open sets. And I take as the basis here the arithmetic progressions in the integers. Does everybody know what an arithmetic progression is? You take any integer, then you add another. You add the same integer over and over and over again, positive and negative. So, you know, like 3 if you're taking 3 plus 5, then you go 3, 5, 3, 8, 13, 3, 8, 13, 3, well, whatever. Yeah, 3, 8, 13. You just keep adding 5s or subtracting 5s. And so you have these progressions. These progressions are infinite sets. And when you look at a progression, suppose you take one progression. This is going to be a set which you're going to use to build open sets. These form a basis for the topology. And it's nice because if you take, for example, the intersection of two progressions, the intersection of two progressions is itself a progression. And if you don't believe that, you can write it down and check it. But the idea is that if you intersect two elements of a basis, you have to be able to find an element of the basis that contains any point in that intersection. But this is nice for arithmetic progressions. So you get this topology on the reals, on the integers. And the nice thing about this topology is that if you take a progression, its complement is made up of if you take a progression where the increment is 5, excuse me, I just moved on. I didn't want to do that. That's my right hand. Stop me if I do that again. If I take any one progression, say I'm adding multiples of 5 to some integer like 0, the other pieces are broken into 4 other progressions. That is, there are a finite number of progressions that are disjoint and exhaust the entire integers for that particular increment. So as a result, these progressions are both open and closed because you have a finite number. The complement of an open set is a closed set, and so you have these progressions are closed and open at the same time. And now, if you look at this family of progressions where you take the primes, if you assume that there are finitely many primes, then these progressions where you take the 0 plus a multiple of each prime, for a given prime, this would be a progression, all the multiples of p. When you do that, if there are a finite number of primes, you have a finite number of closed sets. And a union of finite number of closed sets is closed. So this union of all these progressions with prime increment will give you a closed set. But the complement of this is the set minus 1, 1. That's the only pair of numbers that's not in one of those progressions. And as a result, this would have to be an open set since it's a complement of a closed set. And this is not an open set because it would have to also contain a basis element, and this contains no basis elements. So this is the only thing we could prove all afternoon. Okay, so I'm going to stop and take a breath. We won't prove anything else, but this is just a kind of a curiosity. Furstenberg is a mathematician who's older than I am, so he's pretty old. Okay, number 6. You might well have a handful of knotted DNA if you become a topologist. This is Erica Floppen, who is a professor at Pomona. She was a grad student here many years ago and then didn't get her PhD here. She actually went on to Wisconsin and got her PhD from Russ McMillan at Wisconsin. And she has a nice little book called Topology, When Topology Meets Chemistry, if you'd like to see how topology fits into applications. But I thought we ought to have some kind of an application, and I like the colorful handful of DNA that she has there. Number 5, there it is. You should recognize this guy. Many people would say the greatest mathematician who ever lived. But this gives us some famous theorems, some beautiful theorems. Topology gives us some beautiful theorems, and in particular, I want to talk briefly about one. This is a quote from Hardy. Most of you probably know who G.H. Hardy was, or G.H. Hardy was an outspoken British mathematician who did major work in number theory. He's the one who was the mentor to Ramanujan, brought Ramanujan to Cambridge. And his comment is really, at the end, there's a punchline that there is no permanent place in the world for ugly mathematics. Now, it's up to you to decide what's ugly and what's beautiful. But what I think is beautiful, to me, the most beautiful theorem that I really see is what's called the Gauss-Bonnet theorem. This is Pierre Bonnet, not someone well known, but this theorem is about it has a lot of generalizations and has a lot of more complicated expressions. But this theorem is about a surface, like the surface of this two-hole torus here. If you take something like this, it has a curvature which in some parts like this out here would be positive. And in these saddle points here, and here, and here, and here, and perhaps in some other places like around this kind of saddle here and there, the curvature is negative. And then the curvature can change as I move the surface around a little bit. But what this theorem says is that if I integrate the curvature over this whole surface, I get 2 pi, something we're all familiar with, times what's called the Euler number of the surface. The Euler number of the surface is something that's determined by the number of faces, edges, and vertices on the surface when you break it into simplices and you can count these things. Any one of these surfaces, you can do that. You can break it into pieces. And the beauty to me of this is that on the left, we have something that comes from analysis. This is something that's a numerical function, very specific on the surface. If I change it, I change the function. On the right, we have something that's a topological invariant. If I take two of these that are topologically the same, I get the same Euler number. And so what we see is a connection between two parts of mathematics that's not at all obvious, and it's not clear until you get deeper into the subject as to why these have any connection to each other at all. I think this, to me, is a fascinating theorem. I guess I first taught it in the spring of 1969, probably before some of your parents were born. But I think it's an interesting theorem to look for in the literature. And if we look at this is a little bit of its history. I won't go through it in any detail. You can read it. It actually starts with Descartes, who preceded Gauss. But I think Gauss was very important in connecting it to the idea of curvature. You can state this theorem in terms of a simplicial complex where you don't have curvature, but you have angles around each vertex. Bonnet's role was to generalize it to the situation where you have a surface that has boundary components. Like if you had a tube coming out of here with an edge cut off and a boundary component that was a circle, you can make the same sort of calculation on a more general thing than just one that has no boundary, like the first example. Number 4, we're making progress. It may make you famous if you do your homework. That's this topology. It may make you famous if you do your homework. Now, this is John Milner. Some of you have heard of John Milner. If you've been in my class, you probably heard of John Milner. I think John Milner was the best mathematician of the 20th century. He's still alive. He's at Stony Brook. Amazing guy. He's done amazing work. He writes so well. He understands so much. He solves such hard problems. He's a guy that John Nash felt was really, I guess, hard to compete with, because they were about the same period as students at Princeton. Here's a folk tale, probably false, but I love to keep it alive, so I'm doing that with your graces. The story is that Milner, as an undergraduate, was in a topology class, a knot theory class, that was taught probably by Ralph Fox, because Ralph Fox was his advisor at Princeton. It could have been Tucker, because he would have probably been teaching the same kind of class at Princeton back in the 1950 era. The story is that the question came up, well, if you have a knot, and if you have a knot that is not trivial, that is, I can't unknot it, put it that way. If I have a knot that's a non-trivial knot in 3 space, then the total curvature, if I go around this knot, is at least 4 pi. That I can't have a non-trivial knot in 3 space that has total curvature less than 4 pi, excuse me. And the story is that when this was put up, Milner thought it was a homework problem. It was a conjecture that nobody had solved. And Milner solved it and turned it in his homework. And it was published in the Annals on the total curvature of knots in it was received in 1949. So that tells you about the time he was an undergraduate. But this is one of his earliest mathematical contributions, which deals with the total curvature of knots. Okay, that was number 4. Number 3, it's where the wild things are. This was my move into the bad taste era. Okay. All of you know Maury Sindak, right? Do you know who that is riding the back of that critter? Yeah. It's not hard to tell, is it? Okay. Topology is a place where wild things happen. One of them is probably the most often cited is the Möbius band, or in a more complicated setting, the Klein bottle. The Klein bottle being a bottle that has no inside or outside. You can go from the inside to the outside without crossing an edge, etc. Same thing with the Möbius band. You can traverse it around. You can go from one side of it to the opposite side. They're non-orientable surfaces. The Möbius band can sit in 3 space, but this can't. This has to be immersed. This intersects with itself as it goes through this thing here. To really have an embedding of it, you need to go into 4 space so that you can pull those apart. But the one I want to talk about is the Alexander Horn sphere. This is James Alexander. We won't spend a lot of time with it, but this is James Alexander over there. This is John Conway. You know who John Conway is? Someone's artistic rendition of John Conway with a hairdo of an Alexander Horn sphere. Alexander was a professor at Princeton and did a lot of the early work in algebraic topology. Some of the things in algebraic topology have his name on them, and he was an interesting guy. Besides, Fine Hall was where the math department was at Princeton. In 1969, it moved into a modern high-rise building. And so the building that he was in, that was also called Fine Hall before they moved, was an older, classic sort of building. And he was on one of the top floors of the building, about probably 4th or 5th floor. And the story is that Alexander, who liked to climb mountains, when he left his office, would leave the window open. And so when he came back, he would go up the side of the building and go into his office through the window instead of going through the door. He liked to go to Europe. He was a mountain climber of sorts around various places, particularly around Chamonix. And I didn't know that. I was in Chamonix last summer, and it was a beautiful spot. But I certainly don't want to climb those mountains because they're pretty prohibitive. Okay, so what was the Alexander Horn sphere? He was interested in the Jordan curve theorem. If you think the Jordan curve theorem is about a circle, S1, one-dimensional circle, one-dimensional sphere in a 2-sphere, right? It's in the plane. So I could take the plane in which the Jordan curve sits, and I could take what we call the one-point compactification, pull all the points as they go out in the plane together and put a point at infinity, and that becomes a 2-dimensional sphere. You could do it with a line. Just pull the ends of the line out like this and come up and put the 2 ends of the line together with a point at infinity, and you end up with a circle. So you could think of the Jordan curve theorem as something about the circle in the 2-sphere. Well, he was looking at the question of what about the 2-dimensional sphere in a 3-sphere. That is, look at a surface that's a 2-dimensional sphere, in a three-sphere and ask the same question. Does it separate into two very nice components, blah, blah, blah? Well, he thought he could prove at one point that you had an analog that was very much like the Jordan curve theorem, and then he found that he was wrong. And so he went on to create what's called the Alexander Horn sphere. And let's see if I can get this into action. This should be probably the Alexander Horn orange. Okay. Now, what's going to happen before I this video lasts only about 20 seconds, so you have to watch. Don't doze. You have like feelers that come out from the sphere, and as they approach one another, they split and go like this. And then as they approach one another again, they approach and then they split again. So I'll be quiet and let you observe if I can get it to go. It's a little bit hard to keep track. But it keeps doing this as you get smaller and smaller, and you end up with something that's homeomorphic to the two-sphere. This is homeomorphic to the two-sphere, but it has an unusual property in the sense that it sits in three space so that a ring around this arm here can't be moved out. That is, it's non-simply connected. Its complement is non-simply connected. Does that make sense? That is the outside of the sphere, which when we started was nice and simply connected, right? I could take a circle outside of the sphere and I could contract it to a point. In this case, I can't do that. Too many things here.
Question?
Yeah. Question? Oh, yes.
So the angle by which it separates, like splits, is that deterministic or?
It doesn't matter.
Okay.
When we're dealing with these things, topologically speaking, the angle probably doesn't make any difference at all. I could make them close together. I could make them 180 degrees, as long as they keep meeting and splitting like that. See, here's another picture of it. As these things go up, then they separate into two horns, and then as they get closer, then they separate into two more, and each of those separates into two more, and so on. And you can see this is a circle that's in the complement, that's outside of the original sphere, but it is in a position where I cannot pull it out. I can't shrink it because I have this other piece of the sphere inside, and I can't pull it around because of all this thing I have to pull it through. So this Alexander Horn sphere in 1924 is an example of a bad embedding of the two-sphere in three space. There are various things that have been shown. I think Bing showed that you could take two horn spheres and glue them together and make R3 out of it. So, and then there are other things that we don't really need to talk about. Okay. Oops, gotta go the other way. Oops, that go to that. There, okay. This is another example of the same kind. This is a simple arc, in the sense a simple arc just is a continuous function taking the interval, a closed interval, into three space. And this simple arc has looped around enough times that it has a complement that is not simply connected. So again, I could take a ring around one of these strips here, and I can't shrink that ring to a point because I can't pull it across the curve, and I can't pull the curve around this end because I can't get it through that conglomeration. So this is another kind of an example. There are other examples like this of wild behavior in S3. Sorry. Number 2, it could make you a millionaire, or maybe not. Okay, topology has not made many people millionaires, but maybe a few. This is Henri Poincaré. Some people called him the last universalist, in that he is supposedly the last person who knew everything. Or at least mathematically speaking, he was able to do things in almost any field. And some people would say no one has done as much since then. In 1905, 107 years ago, he posed a conjecture about the three-dimensional sphere, continuing our conversations about circles, two spheres and three spheres. And if I just say it simply, if you had something that looks like a three-dimensional sphere in the sense that it's simply connected and has no boundary, it's compact, it has some of these topological properties. His conjecture was that this was homeomorphic. In topology, homeomorphic is equivalent to a three-sphere. And that is the famous Poincaré conjecture that he wrote in a paper in around 1905. And that was a generator of a great deal of research over the whole 20th century. We could talk about that at some length. I can't ever keep this straight. The first solution in this direction, well, okay, if you look at the analog in dimension 1 or dimension 2, it's easy. The dimension 1 would just be a circle. Dimension 2, it's a two-sphere. In the 19th century, those were known to be, if you converted the statement of the conjecture into those settings, those would be quite simple. But when you look at 3 and higher, the interesting thing to me is that it was solved in various ways at different dimensions. This is Steve Smale, a famous mathematician who got his degree at Michigan and spent most of his career at Berkeley. And he proved this theorem in dimensions 5 and higher. He was also an ardent opponent of the Vietnam War, and is famous for one press conference he held on the steps of Moscow University, where he ripped the U.S. government and the Russian government, or the Soviet government at the time, about the way that they handled foreign policy. Did not endear him to the people in Washington who were funding his research. But he won a Fields Medal in 1966. He was actually here as a visitor one Friday lunch when I was the director of the Dean Scholar Program. I got him to go and have lunch with the Dean Scholars. And I'm not sure they knew exactly what august company they had when they had Steve Smale here, but he's really a nice person, now retired. In dimension 4, it was solved by one of our friends who we would like to have recruited here, Mike Friedman. He was a student in Princeton of Bill Browder in 1973. He proved the four-dimensional case using work with several people. One of them is Andrew Casson, who used to be a faculty member here in our department, went on from here to Berkeley and Yale. In 1969-70, he sat in a class I taught as a grad student at Princeton, so I take a little credit for his success. I'm not sure he would even know who I am anymore, but he now works for Microsoft and does quantum computing. But really, really, really good guy, and a very bright guy. He went to Berkeley for I think a year or maybe 2 years, and without graduating, they said, go on grad school. So he came to Princeton in the fall of '69 and graduated in '73 and eventually settled in San Diego at UC San Diego and did very well for himself. Really, really good mathematician. And then finally, the main conjecture was solved in the last 10 years by Grigory Perelman, Russian, somewhat eccentric, and now somewhat famous for being eccentric as well as for solving this classical problem. Grisha, I think, is what they call him. I don't know him. But he used some algebra, some differential geometry, Ricci flow. Ricci is a name that you see if you study physics, relativity theory, and tensor analysis and such. But Bill Thurston had a conjecture about the geometry of three-dimensional manifolds, and the work that Perlman did was to use some techniques in this area of Ricci flow to prove Thurston's conjecture, and a consequence of Thurston's conjecture was the three-dimensional Poincare conjecture. He declined to take the Fields Medal when he was offered it in 2006. He also declined the $1 million prize from the Clay Foundation in 2010, and this is a quote from him: "And I'm not interested in money or fame. I don't want to be on display like an animal in a zoo." So some of us would be happy to be an animal in a zoo, to have a Fields Medal and $1 million, right? Just put the cage around me. Okay. But you know, he's also very hard to locate. I mean, he lives in St. Petersburg, most people think, either with his mother or in the woods or someplace. So some people, when they try to find him, have very little fortune in finding him. But he's a remarkable talent. Number one, it's right around the corner. Y'all know who that is, don't you? Do you know what the Smith conjecture is? This is Cameron Gordon, whose office is one floor up, 30 feet that way. Cameron is responsible for solving what's called the Smith conjecture. And let me just tell you briefly what the Smith conjecture says. P.A. Smith was a topologist at Columbia, and his main work was on periodic homeomorphisms of surfaces, manifolds, and the like. And he did some very interesting work, and one of the questions that came up is the following. One of his theorems says, suppose I take the three-sphere. Now, here we go back to the one-point compactification. So think of this, where we are now, as a three-sphere. And we're going to put the point at infinity by going in any direction. If we go in any direction, we're going to go to the same point, right? So we're going to add one point at infinity. So if I go straight up and straight down, and I eventually hit the point at infinity, then I'm going to have a circle. Is that clear? So I have a circle sitting in here that includes the point at infinity. Okay. Now, one thing that Smith proved was that if you take a periodic, let's say a period 5 function, that means that if I do it 5 times, I get back to the identity. So it's a homeomorphism, it has period 5, and it preserves orientation, which it has to if it has period 5. But the fixed set is a circle. And if you think of it the following way, think of this as the z-axis, right? I'm sorry, the z-axis keeps moving down here. This is the z-axis. So it's a circle when I add the point at infinity. And if I take the rotation around this, like this complete, I've got rotation through an angle of 2 pi over 5. So I go 2 pi over 5, 2 pi over 5, so on. And back here I have the identity. Now the fixed set is the z-axis and the point at infinity. Everything else has been moving. So the fixed set is a circle in the three-sphere. And what P.A. Smith did was to show that had to happen, that it had to be a circle, the fixed set, no matter how you mess up this periodic map. But the question he wanted to know was, can that fixed set be knotted? If I have a fixed set that's a circle, can it be knotted? And obviously that's something that Cameron is interested in because he does knot theory. And he proved that the answer was it cannot be knotted. The conjecture was that it cannot be knotted, but this was probably, I don't know, 15 years ago, maybe a little longer. There were a number of people who worked on this and who contributed to it. So Cameron is not the only one, but he gets a lot of credit for it, as well as Andrew Casson, who was here. Maybe some of the other people that work in knot theory made other contributions here, but those are the main ones. And so, you live in a world with a lot of topology all around you. Okay. pretty close to the. Okay, now you can ask any questions you want. I may not answer all of them, but I have questions for you too. Would you like to take the quiz?
Sure.
Okay, now from this point on, okay, bets are off, all right? Morong has nothing to do with this, all right? If it's in questionable taste, it's my fault. All right? Here's the first question. Can you name these mathematicians who like to write on glass? All three of them are writing on glass. Can you name any of them?
John Nash.
Okay, let's see. Who is this? Who is this?
That's Nash.
John, who is it?
John Nash.
John Nash? And who is it really? Russell?
Yeah. Gladiator.
Russell?
Marcus Aurelius.
Okay. Who's that? That's Matt. That's Matt Damon as
Goodwill Hunting.
Goodwill or as Will Hunting. Goodwill Hunting, right? Who's that?
He's a very real mathematician.
So Max, yeah.
Yeah, no, that's okay.
He's the ugliest.
Any ideas?
No, is he saying?
That's Carlos Spate, who was my best friend growing up. Okay. I'm surprised you didn't know him. See if you pick him up now. He's number 40. Two captains of the team, two co-captains of the team, both became math professors. You can tell who number 10 is, maybe.
Is that you?
You got it. I just had to figure some way of getting this in here. But we were good friends, and we won district, and we got killed in by-district. Life as a topologist is filled with glamorous people and jet-set social events. This is one of those. I don't think you'll recognize anybody in that picture with one possible exception. But this is my wife actually over here, and she's very neat. Notice how she's catching the ashes from my cigarette in her Budweiser cup. This is a 50-year-old picture. But topology is a lonely deal. Working on topology can be very isolating, and you can feel like you're remote from the world. How have you ever seen that? Sometimes you need to let it hang out and just be a little bit less intense about stuff. This is one of our seminars. Sometimes it gets bad enough that you just like to take a leap. This is the same guy, pictured several times, as obvious. Or take a few people with you. The road to success as a topologist is a very tenuous and sometimes troublesome road, and is not for the faint of heart. But when you get to the end and you stand on top of the world, it's worth all the hard work and becoming a success. So, I'll stop. Any questions? This was supposed to be sort of a change, a little transition into pizza. Any questions? These pictures, okay, let me should give some credit. These pictures with the mountains are from, anybody recognize them? From Norway?
The fjords?
I'm sorry?
Fjords?
Yeah, it's one of the fjords down below, and the Preikestolen, that's called Pulpit Rock. If you go back, it's an incredible. It's an incredible rock, 2,000-foot drop, and no railing. And people go up and sit on the edge. Not me. I wouldn't want to get 10 feet from the edge of that. But it's a spectacular scene called Pulpit Rock. Anyway, this picture is actually a picture that was in the Austin Statesman. Can anybody identify it? ACL in the rain.
Oh, yeah.
Okay. Anyway, we'll stop. Anything else? Hit the light. Okay, questions about anything? Feedback? I'm the only thing standing between you and pizza. This is fun. This talk has been a long time coming. We talked about doing it now for a year and a half. And maybe there's a possibility I'll be phasing out of faculty status, so it may be the last talk like this that I give. So, but it's fun. I'm glad that y'all came. Enjoyed it. I enjoyed doing it, and I hope that it made you a little curious about things in the world of topology. So hang in there, do a lot of good work, and become famous. And don't turn down $1 million when it comes your way. Okay, I guess we can stop. Am I wrong?